let's get this show on the road. We are pretty much, we can't say we're pretty much done because there are so many variations of this darn thing. I tried to think some, yeah, I did that one. Okay, we're pretty much done on these. I'm just going to scan now and do a kind of revision of all sorts of different situations here. So we're going to look at logs, we're going to look at inverse sines, we're going to have a whole look at all the other kind of permutations that could happen. There are so many of them, since you can't cover everything, the best I can do is give you a little smattering of some of the things that could happen. So let's try this one. This one is coming up because evidently I got an email from someone who said it didn't work. And so let's see what this is. This is a natural log of a secant. Would you agree this is a chain rule? It's always useful if you can identify what you're looking at. If it had been log x, secant x, that is not a chain rule directly. Would you agree that is a product rule? So they can look very similar, right? But product rule, chain rule. Well, let's do this one first. As a chain rule, then, it's the natural log of something is 1 over something times the derivative of, in this case, the inside function, secant x. And that's where memory comes in, or at least you've written it down somewhere. What is the derivative of secant x?
Secant x tan x?
Correct. Now, when you write the secant x tan x, if it helps, remember it's on the top. It's on the numerator. Now, if I take this guy and cancel it with that guy, do you see that the answer comes out in a very elegant way? Isn't it just tan x? Now, this fella is a product rule. It's a log times a secant. And I don't expect great things in the style point department, but it is a product rule. So there's a product. If you differentiate a log, you get 1 over x. If you leave this guy alone, you get secant x. You leave the f alone, you get a log. And if you differentiate a secant, you get another secant tan. And what I'm going to do is I'm going to pull out a secant x as a common factor. And that leaves me with a 1 over x, a natural log of x, tan x. So you agree that that's much uglier, and there's really not much you can do after that. You're finished. Okay. Has anybody, because I'm just randomly picking ones as I see them, and almost every question is different from the next one. Has anyone got one they'd like me to do? Because I bet you that would be one others would like to see as well. So is there any in that list that you said, yeah, that one didn't work for me, or I don't know what to do or whatever?
Could we do question 24 on the homework?
Okay. That must be, well, I know what it must be. It's quite near the end anyway, isn't it? Oh.
Yeah, second to last.
I gotcha. I'm getting deja vu on that one, but that's fine. You can, if I do it a second time, I might say it a little bit clearer as well. We have y equals the square root of 1 minus x squared. Take away x, the inverse cosine of x. Right. So this one definitely is, its main feature is it's got an inverse trig function in it, right? This guy, if I just ignore the rest, isn't this guy going to be eventually a chain rule? Right? And so can you imagine there's a little missing invisible dotted line here, right? So I'm just going to concentrate on the left-hand side, and I'm going to call it 1 minus x squared to the half, and don't need that yet. So its derivative is 1/2 1 minus x squared to the negative a half times the derivative of the inside function, which is negative 2x. These cancel and you get negative x, 1 minus x squared to negative a half. That in turn This is me doing nothing but style points, gets you that. And eventually, I get that. Are you happy about the chain rule and then the tidying up afterwards? Are we following each line?
Yeah.
Okay. Now, that minus there, I'm going to give it to the X, and that's just going to make it easier to keep track of the signs. So this is a F times G situation. So I know that this is going to be a product rule. And so the derivative of this piece is going to be F dash G plus F of G dashed. So that's going to be the derivative of negative X, which is -1. Leave this guy alone. Plus minus X, well, it's minus X times the inverse cosine. And the inverse cosine is -1 over the square root of 1 minus X squared, because I told you it is. And this guy is going to be negative inverse cosine of X. And negative X times a -1 gives me plus X over the square root of 1 minus X squared. Are you happy about the product rule and what we got? Now, if I bring this guy down here, I now have this fella, and I have this fella. Where did they come from, Celeste? Okay. So, oh, almost missed it. Doesn't that guy get killed off by that guy? And all that's left is a negative inverse cosine of X. So a little bit surprising. It was the last time I did it as well, but you end up with a very nice looking answer. You might want to have to look into how does WebAssign do this fella, right? So I'm going to try something out right now so that I can figure out myself what WebAssign does, because my version of WebAssign is not your version of WebAssign. It does things differently. You would think it shouldn't, but it does. So what am I doing? 151, okay. So let me, I've changed it to student view so that you can see, hopefully, what I've got. Come on, there we are. So right now you've got this guy in rates of change, so I'll click on that. Well, by the way, your test, your online test is going to be this Sunday. It's just not going to have very much in it, right? Because we didn't get a lot done because of the test and so on. So here is the guy, and I was doing question 24. So here is question 24. Can I make that any bigger? That would be nice. I can, right? So I click on that, and I want to do negative, which is the easy bit. And now I'm going to try and figure out how to do the inverse cos. So I'm going to hit trig function first. And you see they've got a button for the inverse cos. And then I just put X in and I finish it. Right. So there was a button. I'm going to submit that, and it better be right, because if it's not, then it just means I screwed up somewhere. Oh, am I good or am I good? Now, let's show what will happen, and it's very easy to do, is that you type in what you see is what you get, right? So you want to do an inverse cosine, you might hit this button here. Well, you won't hit it yet. Let me take that again. You're going to go cosine, hit this button here, -1, do a bracket, put in an X. That didn't quite work out the way I thought, but there we go. If I submit that answer, it's going to be wrong, isn't it? And if I could put, let's put it here, see if I can get away with it. I can. If I put it here, right, would you agree that looks perfectly correct, doesn't it? It looks just like it should do. But I didn't use the trig button, right? I just did it other ways. What do you think is going to happen when I hit submit? It's not going to like it, is it? Let's prove it. Oh, you little bugger. It took it. Prove me wrong. I thought it wouldn't take it, but that was more amazing than anything. Don't rely on that every time. Oh, well. Okay, I'll give Weber saying the benefit of the doubt. It's not as dumb as I thought it was going to be, right? But I would still, isn't it just easier to hit that button, right? And you've got what you need. So when you're doing anything with inverse sines and cosines, that would be my suggestion. I thought it was going to think I meant 1 over cosine, you know, because -1 meant a power. I thought it was going to see it that way, but evidently it's cleverer than I thought. Is there any more questions that you want me to do from that homework section before we move on to our next section? Although we won't get it finished, at least we'll get the next section started.
Is there any
Right.
chance you could go over number 11?
Sure. Okay, so question 11 is asking us to find the first and also the second derivative. And the function is the square root of x, natural log of x. Would you agree this is a product, Joe? Right, it's not a chain rule, right? So I'm going to rewrite the square root as a half power, which you would do anyway, no matter what kind of rule it was. And now I'm going to identify that this piece is going to be the f, and this piece is going to be the g. So when I do the derivative, which is f dash g plus f of g dashed, I should get it right. If you differentiate this guy, it's multiply by the power, reduce it by 1, times leave the second guy alone, plus leave the first guy alone. And if you differentiate a log, you get 1 over x. And now we have to figure out, is there anything that we can do in style points, right, to make this look nicer, right? Well, would you agree that x to the half times 1 over x can be combined into a single power of x? Would you agree? Single power of x. What would x to the half times 1 over x get you? Well, it would get you 1/2, take away 1. It would get you x to the negative a half. Are you comfortable about that calculation?
Yes.
Right. So what we now have is 1/2 x to the negative a half, natural log of x, plus x to the negative a half. That's a start. The rules for style points are make it look like the original, factor the heck out of it, and if it's a trig function, try and do identities, right? So there are no trigs to worry about. So we've just got factor the heck out of it and make it look like the original. Is there anything here that is a common factor to both those terms that I could pull out?
One over square root x.
Oh, you've done two things at once, which is correct. I'm just going to call it x to the negative a half for the time being. We're comfortable about pulling out the x to the negative a half. And a lot of you did not need half the lines that I write down here, but I kind of feel it's helpful to write all the lines so that when you go back and you say, how did that turn into a square root of x on the bottom, you can kind of see it. So isn't this basically negative powers can come downstairs as positive, right? That algebra trick. And then to finish with, shouldn't I make it look like the original? Are you happy about the first derivative now? Here we go.
Okay. Yeah.
Right. Now, we need to get a second derivative, which basically means we differentiate this guy. Now, if I leave them this way, or if I start with them at least this way, won't I have to call it that guy And if I do, won't this be a quotient rule? Agreed? It's a quotient rule. On the other hand, if I left it as this guy up here, right? So if I used this version, right? That's fine. What rule would I be using to find the second derivative now? That's not a quotient rule. What would this be?
The product rule.
A product rule. Now, I'm not going to do both. Both are correct. Both will get you the same correct answer. It's really, you know, do you like chicken or do you like fish or something, right? I mean, what do you want, right? Do you want to see a quotient rule done version on this, or do you want me to do it as a product rule? Both are going to get the same answer, so it doesn't matter to me.
Product rule would work for me.
Okay, product rule is. So the second derivative is a product rule. It's going to be f dash g plus f of g dashed. If you differentiate this, it's a power rule. So you multiply by the power and then you reduce it by 1. And then you leave that alone. Plus you leave this guy alone. And you differentiate the inside, this function here, not the inside, this guy g. And what do you get? You get half over x, so you get 1 over 2x. And this is negative 1/2 x to negative 3 upon 2. 1/2 the natural log of x plus 1. And if you take this guy and divide it by this guy, can you trust me that you end up with 1/2 x to the negative 3/2? Are you comfortable with this divided by that gets you negative 3/2? Right, negative 1/2 take away 1, negative 3/2. So far, so good? Right. Style points. Can you see any common factor that we can pull out from this expression and from this one? Is there any common factor from this expression that belongs also here? Because I can see one. What is
The
it?
1/2 x to the negative 3/2.
Agreed. Now it gets a bit messy. I almost missed it. You see that negative is still here. And wouldn't this be a plus 1? Now, again, taking it slowly, negative 1/2 log x, take away 1, that's what this is, plus 1. Oh, the 1's cancel, that's good. And negative 1/2 times this gets me negative 1/4, x to the negative 3/2 log x. Are you still with me? Are you happy that that actually comes out relatively nice? But we can still do a little bit more, can't we? Right, remember the other rule is make it look like the original. And right now I don't see any square roots of any kind and I really want to. So I'm going to have this guy in the top, this guy in the bottom, just make the answer negative. What's this negative 3/2 power going to be when it comes down here?
Square root of x cubed.
Wow, yes, you did the next line as well, which is okay.
Oh, sorry.
No, that's perfect. You see how much algebra has been involved in this one question? All the things you have to do to make it work. If you did the quotient rule, can you trust me, you would eventually get the same answer. It might take a different algebraic route, but it's still the same answer. Are we good now, guys? Can we move on to the next section? Do you want to see anything, one last one? Okay, that's good. And give me a few seconds to get out of this one and into rates of change. Now, rates of change is not going to be due this Sunday because we won't get this finished by any means, any stretch of the imagination. But I do get it started, and you should be able to, by the end of today, do some of these questions, the early ones. So your test is only going to be on, it's a pretty big section. Would you agree there was a lot of stuff in that section that we've just done? So it's not like you won't have plenty to do, but at least it's only going to be on that one particular section. So what's the section called? Let's get its number. We're going to be doing section 3.7, which is rates of change. A derivative can be thought of as a rate of change. So if you find the derivative of a function, you can think of it as finding not just the slope of the tangent line, but a thing called the rate of change. So let's give you an example. Suppose I had the height of an object, and the formula for the height of this object was 20t take away 400t squared. And t was time and h was height. Now, if I put that into Desmos, it would look something like this. So it's probably a rocket, right? So I shoot a rocket off and up it goes in the air, and it comes eventually down and it hits the ground. And that's what this would look like. Are you okay with that? It's basically the graph of it, right? Now, suppose I was interested in t equals 2 seconds. And I wanted to know what's called the velocity. Now, the velocity is the rate of change of distance with time. Anybody done physics? Isn't that what velocity is, right? And the units are meters per second, right? Right. So how do you find the velocity of this moving object at, say, t equals 2? Dead easy. The derivative tells you the velocity. So I'll make that function a t. So the derivative of the height function is v of t, the velocity function. That is a very cool use of derivatives, isn't it? You just need to differentiate the position function, right? In this case, it's height. And what do we get? Well, h of t is 20t take away 400t squared. And the derivative at any given time is 20 take away 800t. That's weird. So the velocity at time 2 is 20 take away 800 times 2. That's 20 take away 1600. And the answer I get is negative 1580. And let's pretend the units are meters per second or something. Does negative velocity seem strange to you?
It's just directional, right?
Say again?
It's directional.
Yeah. So I guess that means that it's coming down the way, isn't it? And since this is a rocket, it's definitely coming down at a really fast speed, right? So if you want to find the velocity of any moving object at any given time t, can't you simply just find its derivative at 2 seconds, 10 seconds, or whatever? Now, the one I made up was probably quite unrealistic. So here's an example of a realistic one. the height meters of a projectile shot vertically upwards from a point 2 meters above the ground with initial velocity of 21.5 meters per second is, and if you're not into physics, you don't need to know any physics. All you need to know is that equation. And we're being asked to find its velocity. Well, isn't its velocity the derivative? So differentiate 2, you get nothing. Differentiate this, you get 21.5. And if you differentiate this, you get negative 9.8t. Won't this formula tell you the velocity of this object at any time t that you like? Great. So suppose I wanted to know the velocity at the 1 second mark. Well, it's 21.5, take away 9.8. And the answer I get, 21.5, take away 9.8. And the answer I get is 11.7 meters per second. So isn't it still going up the way? After a second, it's still going up the way. What about the velocity at the 2 second mark? Well, 21.5, take away 9.8 times 2. So 21.5, take away 9.8 times 2. And I'm now looking at 1.9 meters per second. Would you agree that it's still going upwards, but isn't it going upwards a lot slower? But doesn't that make sense? If you throw something in the air, doesn't it go fast, slower, 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 right? And then it reaches the peak. And then doesn't it normally, unless it leaves the Earth's atmosphere, doesn't it now normally come back down again? So what's it doing at the 4 second mark? Well, 21.5, take away 9.8 times t, which in this case is 4. And we're looking at 21.5, take away 9.8 times 4. And the answer is negative 17.7 meters per second. Doesn't that match exactly what you would think an object that you threw in the air would look like? Wouldn't it go like that? At this point in its journey, right at the top of that peak, right at the top, won't the tangent line be a horizontal line? And a horizontal line has a slope of 0, doesn't it? So doesn't that mean that at least theoretically, if you throw something in the air, isn't there a microscopic instant in time where it's not moving? Right, it goes up and then it comes down. But that pause in the second, and it's theoretically, isn't it like a microsecond, right? You wouldn't be able to measure it, but it is theoretically, isn't it stationary for an instant of time? That's kind of cool. Now, if you're into objects moving, there's the original position function. If you find its derivative, you get the velocity function. What do you think you get if you take the second derivative, which is basically the rate of change of velocity, right? It's that guy.
Acceleration.
You do. So that means that if I find the second derivative of this, shouldn't I get the acceleration at any given time t? Okay, well, let's see what that looks like. H is this fella. We found the derivative, which we know is the velocity, and it happened to be this guy. And if we find the second derivative, which is the derivative of the first derivative, aren't we getting what's called the acceleration? And if you differentiate this with respect to t, you get the number negative 9.8. And I know the number negative 9.8. What's special about it?
Earth's
some of you-
acceleration in meters per second.
Isn't it gravity? Isn't that cool that calculus found all those things without you needing to know anything about physics? All I need to know is, where is the object at time t, right? You have to tell me that formula. But if you tell me that, can't I find its velocity at any point? And can't I now find its acceleration at any point? Isn't that much more efficient than the way you probably did it in calculus? You probably did it in physics. Did you do change in position from 1 to 1.1 second divided by 0.1 of a second? Was it some kind of calculation like that you would do? Or you just took a change in position divided by change in time? Nobody's telling me. I'm guessing that's maybe how you did it. Isn't this cooler? I mean, isn't it just pure math? Boom. Newton, who is credited as one of the founders of calculus, used this to understand the motion of objects. And that's why he came out with the planetary motions and why things go around the sun and, you know, gravity and all the other good stuff, right? So he was the guy that allegedly, and we know it's not true, that you get hit in the head with the apple, right? He's that guy. And he thought, I wondered why apples fall to the ground, and he came up with the concept of gravity. And then he came up with, well, how do you find out what gravity is? Because isn't gravity on the moon different than gravity on the earth? Right? And things change. And so velocity is not necessarily a constant. Don't velocities like rockets change their speed, or any object if you throw in the air will change its speed eventually. Is that kind of cool? Let's show you a different application. It's not actually one of those ones. I am going to do this guy. Do you recognize this guy as being a quadratic? Now, it depends on what A, B, and C is, what kind of quadratics do you get, right? If you change them, you get ones that point down the way, ones that point up the way, and all sorts of things. But I'm going to keep that. This one is a bit of a twister for you. That guy there is called a vertex, isn't it? And does anybody know the formula for the x coordinate of a vertex?
Is it negative b over 2a?
You deserve a brownie point. You nailed it. I don't know how many of you remembered that, but she's right. Does it, now that you've seen it, do you say, oh yeah, I kind of remember that sort of, right? You might wonder how they found that for any quadratic in the world, the x coordinate is always negative of that number divided twice that number, right? Let's show you how you can do it. Let's find the derivative of this, right? Now remember, A, B, and C are just numbers, right? Constants. So if you differentiate this, you multiply by the power and you reduce it by 1. What do you get if you differentiate bx?
b?
You get b. And what do you do, or what do you get if you differentiate a number plus c? What do you get if you differentiate plus c?
0.
You get 0. Now, okay, that's the derivative. In this case, I'm going to use the derivative as measuring the slope of the tangent line. Would you agree that at the vertex, the tangent line is a horizontal line? Does that make sense? And horizontal lines have a slope of 0, don't they? All of them. Can you see where this is going? If this is 0, then when does this happen? Well, let's find out by solving for x. I'm going to take away b from both sides. And then I'm going to divide both sides by 2a. The x coordinate of the vertex of any quadratic is going to be negative b over 2a. Is that not kind of cool? And if you can't remember that guy, can you at least use calculus to find him again? When I was at school, you probably believe it because you know what my memory is like. I have and always had an atrociously bad memory. My memory is, I can't remember people's names. To this day, I'm very bad at remembering people's names. But God gave me one gift, well, apart from enjoying math, which I do, and I can remember how to do things. So if I ever forgot what the x coordinate of that vertex is, which no, I do memorize because I've been doing it for something, but if I forgot, I would know how to find it. And calculus was my go-to guy for finding all sorts of things that I couldn't remember on the spur of the moment. You know, when you're doing an exam and I never got open book, so I had to do, you know, if it wasn't in my head when it came in, it wasn't going to happen, right? So you had to memorize tons of things in the old-fashioned day. And so having such a bad memory, I had to find workarounds. And all I did is I just memorized how to get them. And normally it was pretty quick. Are we good so far? Again, if you don't take physics or is it mechanics, I'm not sure what class it's in, this doesn't matter. The calculus will take us. Does anybody recognize this as a version of the formula for the position of an object with an initial velocity of u and acceleration of a? Do you recognize that guy, or at least a version of it? I am going to find this guy's derivative. Oh, but that means velocity then. And if you differentiate ut with respect to u, and if you differentiate this with respect to t, and if you differentiate this, you multiply by the power, and you get u equals at. Do any of you recognize the velocity of an object whose initial velocity is u and whose acceleration is a? You see, I've now created a new formula. If you took any formula that you have found in physics, mechanics, chemistry, engineering class, take any of those formulas, as long as there's only one variable, in this case t. If you differentiate that thing, you are finding the rate of change of this thing with time. And that very often will be velocity, or, you know, in electronics, if you do the rate of change of, oh God, what is it? I think if it's the rate of change of volts with time, you get amperage or something, right? You'll find some formula that is actually quite useful. Any questions? You see what we're trying to do here is say, look, this calculus stuff you can actually use in other places, right? It's not just mathy things that you just get an answer but nobody uses it, right? Let's try this one. This is another, this is a version of question 2 now. This is an object, its position function S is given by 96t take away 16t squared. And we're being asked to find the velocities at various places, or heights, or when it hits the ground. So let's do the first question. First question is, what's the maximum height? So how high up does this object get? Now, if you put it into Desmos, it would look like that, because all of them do. Aren't we trying to find that number there, right? How high does this ball go? Now, you could do it with 142 or 141 stuff. Couldn't you just find the coordinates of the vertex and the y coordinate would be your height? But let's do it with calculus instead. If you differentiate this function, you get 96 take away 32t. So far, so good. Now, the height, isn't the derivative going to be 0? We talked about that before. Great. Now, if I solve for t, in this case, it's probably easier just to do that. Are you happy that t is 3 seconds? And what's the height at 3 seconds? Well, it's 96 times time, take away 16 times time squared. So it's 96 times 3, take away 16 times 3 squared, which is 9. And the answer is 144. I think it's feet. Is it feet? Let me check. Yes, it is. So I know that this ball, 144 feet, or this cannonball, whatever it is, right? 144 feet. Don't I also know for free, even although they didn't ask me, don't I also know that it happened at the 3-second mark? Now, the second question, this is going to be our last question for today. There's a B and a coming up now. What is the velocity of the ball when it is 128 feet above the ground? And the other question is, what's the velocity of the ball when it's 100 on its way down? Ah, okay. So at the 128 feet mark, can you pretend that's 128 feet? At this point here, isn't it on the way up? And then at this point here, isn't it on the way down, right? And we're being asked to find what's the velocity when the height is 128. So you've just told me that S is 128. So I'm going to find 96t, take away 16t squared, and I'm going to make it equal to 128. Would you agree that's a pretty horrible quadratic equation to solve? Great. Wouldn't you like an easier way to solve? I don't see too many people saying, yeah, I'd like an easier way to solve. I would like an easier way, even if you don't. So I'm going to show you how to do that using Desmos. And close
So
this
you
off.
don't put the derivative of the equation equal to 128?
No, because that would be the velocity at 128 seconds, and that's not what we want. Or that would be the velocity, that would be when does it have a velocity 128, I think that would be in the case you've got. You're going to have to just hang with me for a few seconds. I have to load the damn thing up. Okay, we've got Desmos up. Yes, we do. I'm going to go in now and show you Desmos. Now, though you can't see it, the quadratic was 96, I think it'll take t, take away 16t squared. If it doesn't do that, I'll change it. Oh, it does, right? Okay, really horrible scale here. So I'm going to go in here and change the x's, essentially the horizontal axis. And I'm going to change it from 0 to some reasonable number, probably say 4. Okay, how about 6? There we go. Right. So I should now be able to shrink this back a bit. There, can you see the ball going up and the ball going down? Right. Now we want to find out right now what time, right? Will it equal 128? So I just type in y equals 128. Now, do you see that the horizontal line is the height and the red line is the ball? Aren't I interested in there? Oh, that happened at the 2-second mark, didn't it? You see it? 2 seconds. And on the way down, 4-second mark. So t equals 2 and t equals 4. Would you agree that was probably a lot less work than trying to solve that same equation algebraically? Right? Can you imagine trying to solve this, how hard that would be? Isn't it easier just doing it in Desmos, right? So I know what the 2 times are. The first question is on the way up, which is that one. And the derivative is 96 take away 32t. So at the 2-second mark, it's 96 take away that guy, which is 64, which I believe is 32. And on the way down, it's the derivative is the same each time, but on the way down, it's 96, take away 32 times 4. And I believe that is negative 32. And the units are probably feet per seconds, if you can't read that scribble. Let's see if that makes sense. At the 2-second mark, which is here, this is going up at 32 feet a second. And at the 4-second mark, which is here, isn't it coming down negative 32? Does that make sense? Does it also make sense that they're the same number? As long as friction and all sorts of other things, air, pressure, whatever, don't get in the way, right? If it was a perfect vacuum, wouldn't something come up and come down with the same kind of velocities? Right? If it were not with 20, it would come down with 20. And that's what we've discovered. And say your last name and bye-bye. I'll hang about for anybody. You will not be able to get...
Thank you. Bye-bye.
Bye-bye. You won't be able to see your test, your online test, to later this afternoon. Well, more likely early this evening. So around about 4 or 5. Okay, so I don't think you're looking to find it that early anyway, right? But for those who have to do it early. Okay, I'll hang about. Question. I have a question.
Yes. I was just wondering if you could just go over that number 8 again.
Is that is it the one that I did earlier today? Or not?
No, you did it yesterday.
Okay, we can do
something-
that. Not a problem. So
Oh, good.
have you got it handy? Otherwise, I'll go and look. Have you got your version handy? I guess that's what
I've got it.
Okay,
It
what does it
is
say?
T to the Z is,
So is it y equals?
I'm sorry, T of Z equals 6 to the Z,
6 to the power of?
yeah, to Z.
Right.
Mhm. Log base 6 of Z.
Okay, so we got this combination of logs and exponentials, and they hopefully play well together, but they also play differently, right? They work on different roles. I'm trying to see if I can find my little formula sheet to show you where I'm getting the derivatives of each of these. And I shouldn't have thrown it away yet, so if you can bear with me for a little while. Here we go, I found it. So first thing I'm going to do is I'm looking at this question, and what I see is a product term. Are we good? Is that what you see?
Yeah.
Right. So the derivative is f dash g plus f of g dashed. So far, so good.
Yes.
Now, if you differentiate 6 to the z, it's this guy here. And the derivative of 6 to the z is the natural log of 6 times 6 to the z. So I'm using this rule here where a is a 6. So far, so good.
Yes.
That's f dashed. Then you do g, which is the log to the base 6 of z.
Okay. Got it.
Plus 6 to the z.
Yeah.
And if you differentiate the log to the base 6 of z, we're looking at this guy up here, the log to the base 6 of z will be 1 over the natural log of 6 times z. So that's f dashed, that's g, that's f, and this is g dashed.
Okay. And I'm not multiplying it with the derivative of Z.
Which is just 1.
Oh, I am. Okay, it's just 1. Okay. Got it.
So I'm now going to go hunting for tidying up. The only common factor I can see right now is the 6 to the z. So I've got the natural log of 6 times the log to the base 6 of z plus 1 over the natural log of 6 times z. So far, so good?
Yes.
And if you put that into WebAssign, it might or it might not accept it. It is correct, but there are different versions of what that looks like. Have you tried putting that version in yet?
6. No, because it's different than, no, I did have different other answers and I said, oh, I've only got 3 left. I gotta ask a question. so,
Okay, so
Yeah.
what I'm going to do right now is I'm going to go in and see what WebAssign is expecting, because this guy here can be turned into the natural log of Z. And that's why I want to see whether it did that or not before I tell you about it. So I'm loading up as we speak. There we go. I'm going to find your specific one. That way I know. What's your last name again, Rachel?
Bell, Bell.
Gotcha. Right, and this one is in logarithmic, correct? So
Yes.
let's
Number
look at
8.
number 8. So I'm going to question 8 as we speak. And they did. This piece here is the natural log of Z.
The whole thing?
Yeah. So the natural log of 6 times the log to the base 6 of Z is the same thing as the natural log of Z. And if you want to go look for, the math of why that works, it's called the change of base.
I heard you say that yesterday when you were explaining it and I wasn't sure, so I'll look that up.
Right. Basically, it's, you can take this formula and write it 3 different ways. And that's the way I've written it right now. You can also say that the log to base 6 of Z is a natural log of Z over the natural log of 6. That is the same as that, just written in a different way. So you're more likely to see it written like this than as that. But these are equivalent. And if you take this and write it as that, can you see that these two guys now get combined to that? What I'm going to try and do now, well, since we know this is the right answer, have you got yours?
I would say put that in because that was actually one of my answers was natural log of Z over natural log of 6 plus 1 over Z and then the whole thing multiplied by.
Oh, so you
6
did put this version here in?
I put the lower one.
You put this one in? I'm not
No.
convinced that you have. You may not have typed in the right button. Let's see if I can go in and do a student version of that same question then.
Yeah, I don't know if you can go into mine and look at previous answers, but then you'll know.
Well, I'm just trying to figure out how this gets typed in for the future for you as well. So right now I keep picking the wrong darn choice. It's WebAssign I want. There we go.
Log.
So I'm going to go into that question and type in both versions. Well, one version first, and we'll see if WebAssign is happy with that particular version, right? So let's go in.
Okay. I see how you canceled out the natural log now. I see. Oh, so I did not put in that answer correctly.
Okay, so out of curiosity, I just want to find out whether WebAssign will take this or whether it must be that way. Because based on what I did with inverse sign, it took both, right? And I thought it would only take one. So maybe we'll get lucky and it will take this one. And if it does, then that's great. So I can only do my own version, but that's fine. The only difference will be that that'll be another number, but the question will be pretty much the same guy. So let me show you what I've got and we can check it out. Basic on, right, there we are. And you see mine has a 7 in it, okay?
Okay.
but I can tell that all the 6s become 7s. So it should be 7 to the power of z for my question. So 7, hit the button to the power of z,
Mhm.
a bracket. The natural log, let's find natural logs under functions maybe. Yeah, the natural log, just in case it needs that as well, of 6 times, oh, the log to base somebody is the one underneath it. So the log to base 6 of z. Right, so that's, oh, shooting space. I should have hit a bracket somewhere and I forgot to. So the natural log of 6, finish the bracket. That's weird. Okay, there, that's better. Times the log to the base, there we go. The log to the base 6.
7.
Oh, 7.
Everything.
Oh, 7, you're right. Everything should be 7. You can tell it's the end of the week, can't you? It's 7. And then inside that, there was a Z.
Mhm.
And then I think I need to finish with a bracket again. Yes, I do. And then I'm going to do plus. It's going to be a fraction this time, isn't it? So where's the fractions hiding? Here, here. So it's going to be a fraction. And on the top, it's going to be a 1, a natural log of 6,
Mhm. 7.
7, natural log of 7. I keep looking at my answer down here as well, which doesn't help. The natural log
Yeah.
of 7. Make sure I don't have too many brackets with a Z.
Okay.
Please work, otherwise I'll have to change it to the log Z thing. No, you know, it's not biggie, but. Hey, it takes it. You don't need to know the log Z thing, which is what I
Okay.
would prefer.
I'll probably look it up anyway, but that is helpful. I appreciate that. So,
Not a problem.
okay. Thank you.
You're
and
welcome.
Have a good weekend.
You too. Have a great weekend. Teresa, you got a question or are we out of here? Oh, Rachel, can I keep this as part of the lesson so people could watch what we did? Do you mind?
Yeah, no, that's fine.
Okay. Teresa, are you just forgot to switch off? She probably forgot to switch off then. Right. Bye-bye, everybody.